All right. A warm welcome, everyone, to our webinar. My name is Shani Prince. I'm heading the life science team here at KNIME, and I have the pleasure to introduce you to our speakers today, Artem and Greg. I think most of you know Greg already as our chemoinformatics wizard and father of RD-Kit. And Artem actually also has a background in the life sciences, so he has a PhD in biophysics. And he now works as a data scientist at our partner Redfield, where he, for example, also contributed to another project about data anonymization, which we can actually learn more about on Tuesday in another webinar. But today we want to talk about a cool set of nodes that Redfield developed to perform conformal prediction. It's a very cool algorithm that allows you to make predictions at a user set confidence level or error rate. And Greg will actually first give us an introduction into the method, and then Artem will demo the workflow and show us the nodes. Before we dive into that, just a little bit of housekeeping. So before we start, that session is recorded and will be available on YouTube. We will also share the slides with those participants of the webinar. And please use the Q&A section to post your questions and upvote your favorite questions. You can actually find the Q&A sections in your Zoom window at the bottom, and then you can upvote your favorite questions with the thumbs up, and this way we can actually make sure that especially the most pressing questions for sure get answered. And with that, I hand over to Greg. Welcome.
Thanks, Johnny. Hopefully my screen is now being shared. Great. Okay, as Johnny already mentioned, Artem and I are going to tag team this. So we'll do a mix of slides at the beginning, and then Artem is going to do a live presentation. We'll start with Artem saying a few words, and then I will do an introduction to conformal prediction.
Yeah, hello everyone, and thank you for attending conformal prediction webinar. Just let me introduce myself. So my name is Artem Ryasik. I work in Redfield as a data scientist, and Redfield is an IT consulting company based in Stockholm in Sweden. We are experts in cloud solutions, data warehousing, graph databases, and KNIME data science projects. We also provide training courses, 9 training courses in Nordic countries, and we develop KNIME extensions. Next slide, please. Yeah, so this is just a short description of our company. Yeah, and let me just introduce you this shortly the extensions for KNIME that we have developed. Next slide, please. So as long as we are working with graph databases, we have developed an integration for OrientDB, a graph database, so you can easily work and process your data in OrientDB. You can do ETL processes, and also we are developing Neo4j extension, and we are planning to release it this summer. So if you are a graph database expert, probably you will be interested in these extensions. Next slide, please. So yeah, conformal prediction extension. This is an advanced algorithm that allows you to better analyze and understand what's hidden behind the scenes of your supervised machine learning classification algorithm that is going to be presented today. Next slide, please. Yeah, and our third released extension is privacy extension. So we are going to present it next week. So if you're interested in data anonymization and GDPR issues, please join us next week. Yeah, so that's all about my introduction and introduction of Redfield. So Greg, please.
Thanks, Artem. Okay, so what I'm going to do is what I will call a gentle introduction to conformal prediction. By gentle introduction here, I mean that I'm going to skip the math and work my way through an example. So I'll provide a qualitative overview of the method and work through an example of how conformal prediction works. I'm going to start with some acknowledgements. So Ulf and Johnny were integral in me finally gaining an understanding of this method, at least I hope I did, and in putting together the deck that you'll see now. And we should, all of us, be grateful to the person who actually did the work to write the nodes that provide conformal prediction inside of KNIME, which is Alexander. He's at Redfield, as Artem already mentioned. So let's start with talking about why you might want to do conformal prediction. And in my mind, there are really three things that make this an interesting approach. The first is that it gives us a statistically sound measure of prediction confidence or significance from a machine learning model. And this is different from what you normally get from your machine learning approaches. So for example, a random forest and KNIME gives you predicted probabilities for each of the classes in the classifier, but those don't give you a hard confidence estimate. So if the model says there's a predicted probability of 0.8 that a particular row is class 1, that doesn't mean there's actually an 80% chance that that prediction is right. And conformal prediction, within a few approximations that we'll explain along the way, actually allows you to give hard confidence levels on your predictions. It also lets us set the target error rate that we're willing to tolerate when we're making predictions, and to know, again, within the assumptions of the method, that we will actually achieve that error rate. And finally, and I think this is one of the really great strengths, particularly in KNIME, is that you can use conformal prediction with any machine learning approach that gives you predicted probabilities. And you can do that without having to modify or retrain the models themselves, which is really cool. So if you have a workflow setup that builds a gradient boosting model, you can do conformal prediction with that. If you're doing logistic regression, you can do conformal prediction with that. I'll show you random forests. What do we need in order to be able to get all these benefits? There are two things. We need exchangeability of our data set and a measure of non-conformity. Exchangeability means that the ordering of the observations in the data set is not important. And this is nice. It's weaker than the usual IID requirement that we have in machine learning algorithms. So we don't require that the testing and training data come from the same distribution, but instead we require that there's the same relationship between the inputs to the model and the outputs. So the connection between inputs and outputs of the training set is the same as the input and outputs of the set of rows that you want to predict later. Non-conformity is a somewhat different thing, something we're not really used to thinking about. And it's a measure of how strange an instance in prediction is relative to the things that we've seen so far. So if I give you a new row to predict, or if I give the model a new row to predict, I would like to be able to know how strange that is, or how different it is from the instances and predictions that that model saw when it was trained. And there are many, as you can imagine, there are many, many possible ways to define that. What we're going to do here is use the machine learning model itself and use the predicted probabilities that come out of that and assess how strange or how non-conformal new row is by comparing the predicted probabilities with the predicted probabilities of those in the training set. So let's get to a specific example. I'm going to build a model for the data set that's described here. The details of the data set and the model are not incredibly important. This is a data set drawn from Campbell, which is a large open data source of bioactivity data. We have a classification problem. So the data set is divided into two classes, toxic and non-toxic. As you can see, it's imbalanced. So there's 163 toxics and 510 non-toxics. We split the data into three sets instead of the usual two. Really, we split into two first, a testing set and a training calibration set. And then we split that training calibration set into two further sets, training and calibration. This is the breakdown that we're going to use here. So 430 training points, 108 calibration, and 135 testing. And we do that split randomly, but stratified. So there's the same distribution of toxic and non-toxic in each of the sets. We build a random forest. And as I mentioned already, the conformity measure that we're going to use is the predicted probabilities from the random forest. How do we do that? What we start by doing is build the random forest with the training set. Then we take the calibration set and we get predictions for each of the rows of the calibration set from the random forest. We divide that calibration set into two pieces. The first is a table of the rows that are actually in the toxic class, so really in the toxic class. And the second is the table of the rows that are in the non-toxic class. And then I just generate predictions for each of those, take the predicted probability that they're, for the ones in the toxic class, the predicted probability that they're toxic, for the ones in the non-toxic class, the predicted probability that they're non-toxic, and then sort by that predicted probability to rank them. So these are our calibration tables. We have, again, the predicted probability of toxic for every compound that actually was toxic, and predicted probability of non-toxic for every row that actually was non-toxic. Using these two different tables to do calibration is a characteristic of an approach to conformal prediction called Mondrian conformal prediction. The term is down at the bottom. And this, everything else that we'll do throughout the rest of this is Mondrian conformal prediction. Okay, let's look at how we actually generate a prediction. So I have a new compound that I want to predict. It's drawn here. I give that to my random forest, and the random forest says the probability of being toxic is 0.45. The probability of being non-toxic is 0.55. Normally, if I was using the predictions from the random forest, I would say, okay, this compound is predicted to be non-toxic because probability of non-toxic is probability of toxic. If I were looking at those, I would say the model's not really certain, right? There's some uncertainty about the result, but it is non-toxic according to the prediction. In reality, this compound is actually toxic, so that prediction would have been wrong. What is conformal prediction, or how do we do a conformal prediction for this? So we take our predicted probabilities and we go to our calibration tables, and I take the probability of being toxic and I look that up and find where that sits in the calibration table for toxics. So 0.45 sits here at rank 3. 0.55 sits in a non-toxic table here at rank, I can't see it because Zoom is covering it, at rank 68. So now I have the ranks of the two compounds for the toxic and the non-toxic. Once I've done that, I can calculate p-values. I'm not going to get into the details of the p-values here, but I'm happy, if there are questions about it, I'd be happy to explain how this is done during the Q&A session. But the p-values I get for the p-value for toxic is 0.85 and the p-value for non-toxic is 0.17. So now we have p-values. These are what we're going to use to actually make our prediction. So to make the prediction, we pick our target error rate. This is the significance level, and this is what you'll see in the KNIME node. And then to actually do the prediction, I take the p-value for a particular class, and if that is larger than or equal to the significance level, then a class is a member of the prediction set. So in this particular case, if I pick target error rate of 0.2, the p-value for toxic is 0.85. That's larger than 0.2, so toxic is in the prediction set. 0.17 is not larger than 0.2, so non-toxic is not in the prediction set. If I really want to be certain about my predictions and say my target error rate is 0.1, so 10% maximum error, 0.85 is still in the prediction set, but now 0.17 is larger than 0.1, so that shows up too. This fact that we get a prediction set instead of an individual prediction is one of the characteristics of the conformal prediction. And we'll explain what to do with these in a couple more slides. Here's another example. This particular compound, from the random forest, the probability of toxic is 0.39, which translates into a p-value for toxic of 0.2, and the probability of non-toxic is 0.61, which translates to a p-value of 0.7. So here, if I were to take a target error rate of 0.2, the prediction set would again include both toxic and non-toxic, because both of these values are greater than or equal to 0.2. One thing that's worth mentioning, I was not able to find an example for this particular model and this particular data set with reasonable threshold values, but it is possible for the model to generate an empty prediction set. So for example, in this made-up case, if p-value for toxic was 0.26 and p-value for non-toxic is 0.35, we had a target error rate of 0.4, the prediction set here would be empty. So there's three kinds of prediction sets you can get. You can get a prediction set that includes a single member, a prediction set that includes multiple members, or a prediction set that's empty. Okay, what we've done so far, I was walking you through using a single training calibration split. So I took my data, I split it into the training and testing, and I split the training calibration further into training and calibration. The conformal prediction is done using this calibration table. For any reasonable size data set or realistic size data set, the quality of the conformal prediction is going to be sensitive to this split. So if I do a different random split, I'll get different conformal results, unless the data set is very large. That's a problem. So the way we work around that problem, as you might imagine, is we do this multiple times. And we switch from doing Mondrian conformal prediction to Mondrian cross-conformal prediction. So we take that training calibration set and split it multiple times into training calibration pieces. And for each of those, we generate a model. For each of those models, we generate a calibration table, and we save all of the models and all of the calibration tables. And at the end, when we want to make a prediction, we generate p-values from each model and calibration set, and then take the median p-value in order to get the prediction. So that median p-value is compared to our target error rate and gives us the actual prediction. For the example we've been looking at so far, the median p-value for the first compound ends up being 0.83 for toxic and 0.1 for non-toxic, and the median p-value for the second compound is 0.1 for toxic, 0.83 for non-toxic. The fact that these are the same but reversed is a pure coincidence. It's an unfortunate property of the example that I chose. I apologize for that being confusing. But again, so now we have these median p-values. If we actually want to generate predictions, we just compare the p-values to our target error rate and are able to make the predictions. Okay, so now we know how to generate robust predictions. How do we evaluate the performance? The first thing is to understand what it means to be correct for a conformal predictor. And the definition within the ansatz is that a prediction is correct if the prediction set includes the actual result. So if the result, if the thing being predicted actually is toxic, the prediction is correct if the prediction set is toxic, or it's correct if it's toxic and non-toxic. Similarly, for non-toxic, it's correct if the prediction set is just non-toxic, but it's also correct if it's toxic or non-toxic. The empty set is always wrong. So this is the ansatz for correct. The prediction set includes the actual result. Using that, we can then define a couple of interesting metrics to understand how well the conformal predictor is doing. The first is efficiency, and the second is validity. Efficiency is the fraction of single class predictions, and it ignores whether or not the predictions are correct. So it's how often the model gives you a single answer, not a gives you a prediction set with a single element, not multiple elements. And validity is the fraction of predictions that are correct within the ansatz that we're talking about. We typically calculate this per class and then do an overall value based on the weighted sum of those, weighted average. Here's an example for the toxic, non-toxic thing we've been looking at. So here's a set of actual values along with the prediction set that was generated for them and whether or not they're correct. So again, if the actual value is toxic and the prediction set includes toxic, it's correct. If the actual value is non-toxic and the prediction set does not include toxic, it's incorrect. Using the results we have here, we can calculate efficiency. So if we look at the actual toxic rows, one of those includes only a single member in the prediction set. It's this one. So the efficiency for toxic is 1 out of 3. For non-toxic, 5 of those rows only include a single member, so 5 out of 7 are there. So the efficiency for non-toxic is 5/7, and for toxic it's 1/3. The overall efficiency is just the sum of those, so 6 out of 10. Validity, these are looking at the predictions, the fraction of predictions that are actually correct. Again, correct, the prediction set includes the actual value. So for toxic, it's 2/3, so that this includes, this toxic prediction is correct, and this toxic prediction is correct. And for non-toxic, it's 6/7, so the overall, it's 8 out of 10. So we have those two measures to evaluate the performance of the results. I'm introducing all of these because we'll see all of these when Artem actually shows you the nodes. So you'll see the target significance level, that's the error rate that you're willing to tolerate, and you'll also see the efficiency and validity. if you want to learn more about this, again, this was a general introduction and included basically no math. If you want to learn more and see some math, there's a great tutorial by Schaefer and Wolf on conformal prediction in the Journal of Machine Learning Research. There is a really good tutorial introduction and a presentation from Ulf, presented at UK QSAR in 2018. It's linked here. And then the last example is a quasi-random example I picked of one of the applications of this Mondrian cross-conformal prediction approach to real-world data sets in the drug discovery context. It's shown here. The first two of these are freely available. The last one, unfortunately, is behind a paywall. I apologize for that. Good, so that's the gentle introduction. Now let's move on, and Artem will actually show you how you do this in KNIME and how this all actually works. And I'll hand it over to you, Artem.
Yeah, thanks, Brett, for this nice introduction. Okay, I guess, yeah, my screen is visible. So I have seen some questions. So these notes are free, and this workflow that we are going to look through today is already available on KNIME Hub. So if you would like to follow what we are going to do in the next 30 minutes, please download this workflow from Hub. It's called Conformal Prediction Workshop. Yeah, so let's just let me first describe the data that we are going to work with today. So this is an example from chemistry, and Greg helped me with this data set. So let's just take a look on this. If you're not chemists or you don't have any background in life science, please don't worry. I will try to make the explanation quite straightforward, even if you're not expert in this area. Anyway, so today we are going to consider the binary classification problem. However, these nodes are not tied to number of classes. That there is no limitation for the number of classes that you can apply. So it could be 3 classes, it could be 10 classes, as many as you might have in your data set. So the main columns that we have here is the smiles. This is just the way how to represent the chemical compounds. Basically, this is a representation of chemical formula of the compound. Then we have a compound ID. It's an individual ID for every substance, for every compound. The assay ID is as a group of the substance that substance belongs to. And another useful column that we're going to use is activity comment. So this column will be used for producing target variable. So let's just quickly go through the pre-processing step. So this is a routine for every data science project. So first of all, we are going to filter out some specific, only one specific assay. So it's just simple. We use a raw filter, take only compounds that belong to this assay. Afterwards, we use this RDKit nodes for processing this chemical data. So first of all, we are going to strip the salts of the molecules. So if you're not a specialist, you can just consider that this is just another way of additional filtering of the data. So we are using predefined strategy for desalting. We are not providing any additional inputs to this port. Finally, we generate fingerprint. Fingerprint is just a special format of representing the features. So imagine that instead of having several hundred columns that represent features, we just have this one vector, which is extremely long, but it contains everything we need. And this is basically a Boolean vector. So 0 and 1 means that some feature present or not, and that's it. So fortunately, this format is very well supported in native KNIME models. So this vector basically will be our only feature. However, in general, it represents a lot of features. So the next, we just filter out some some null values that we get for fingerprints. The filtering strategy is very, very simple. And then we get rid of some columns that we don't need anymore. And the final step of data preparation is basically engineering the target variable. So it's fairly simple. We use rule engine node for this. So if the comment contains the word active, no matter what case it is, we consider this sample to belong to class 1 or class -1, vice versa. So basically, we're going to predict whether the substance or compound is active or not. So it's pretty straightforward. It's a binary classification case. Before we jump into conformal prediction, let's just take a look, just have a overview of the data set that we have. So as you can see on the class distribution, so we have 49,000 samples, and 43,000 they belong to class -1. They are not active, and only 5.6 thousand records belong to class 1. So this data set is quite unbalanced, and this is actually good for the demo, because it's one of the advantages of conformal prediction, that it still can provide you sustainable predictions even for unbalanced data sets. Okay, so the data preparation step is over. Now we are switching to conformal prediction. So as Greg previously explained, we need to split the data set not into 2 subsets as we usually do for supervised machine learning, but into 3 subsets. So for this purpose, we are going to use this consequent node partitioning and the conformal calibration loop start. So first of all, we split the data set into training and test data set. It's typical for any other supervised machine learning problem. So as long as our data set is unbalanced, we need to keep this ratio between classes. So we are using stratified sampling over target variable, and we are going to put 80% of the samples to training set and the rest 20 to test data set. Fairly simple. Then we are going to training process, and here we need to split our data set one more time. So as you can see, we are splitting the training data set, and as long as we are going to train multiple models in order to obtain multiple calibration tables, we are going to use this loop. So these nodes are part of the extension. So let's see the settings of conformal calibration loop start. And actually, it's almost the same as for partitioning nodes. The only difference here is that you can set up the number of iterations, basically the number of how many times your data set will be reshuffled and partitioned during every iterations. So here we are using, I selected 3 times. So basically it will produce, in this loop, I will produce 3 models and 3 calibration tables. But please pay attention that this data set is quite big and training process takes some time. So run this with discretion. Or maybe you should decrease the number of iterations. Yeah. Then we are going to just use casual random forest node, native KNIME node. So the settings are pretty straightforward. So the target column will be target. It has the same name. So as you can see, it supports these special fingerprints format. So those of you who work with in chemistry and probably using this feature, you know this, but basically everything we need is included into this one feature. And before preparation for this workflow, for this webinar, we did some estimations and we picked these parameters to be the best. So we are going to train 300 models, and the tree depth is going to be 64. So I have already executed the workflow to save some time, but on my computer, it takes about 3 minutes to train just one model. So if you're going to repeat it just right now. Yeah, afterwards, we trained a model. We were using a calibration set to produce the calibration table. So we feed this data set into predictor node, and in the settings, please pay attention that you need to activate this checkbox. This node must return you the individual class probabilities, because in the current implementation of nodes, class probabilities are used for ranking, are used for calculating p-values. Then you need to feed the output to conformal calibrator node. So let's see the configuration of this node. Again, it's fairly simple. You need to select the target column with real values. And then you can select whether you would like to keep all the columns that you have put in with input table, or you can select which column will be used as an ID column. So in our case, it's a compound ID, and I'm going to skip any other columns. So what this node does is that it basically sorts that table by class and by class probability in descending order. Let's just briefly take a look on the result. So if I would, so here we have it. I sorted by target, and we see class 1 and the probability of this class. So the higher the probability, the higher the rank. And the same in the end, I have this kind of transition. So now I have class 1, and it's also sorted regarding class 1 in the same order. So now we can have to consider the probability for class 1, and it's also sorted in descending order, similar way. So and one more thing. So we need to keep together calibration table and the model that was used to produce this calibration table. For this purpose, we are going to use this model to cell node. What this node does, it basically serializes KNIME model into KNIME table. So if we would take a look on the input, it just says that it's some kind of objects. And here we have a brief description. So 300 classifiers, 300 trees for 2048 attributes. So a good point about this node that it's compatible with all models that are produced in KNIME. It could be native KNIME model like random forest or gradient boosted trees. It could be neural network. It could be PMML model. And I did some tests. It could be even H2O model. So this node seems to be compatible with all types of models available in KNIME. And finally, in a conformal calibration loop end, we just aggregate obtained models with calibration tables. So there is no settings in this end node. What it produces, however, is additional column for every table. So this is just a number of iteration. However, this column is used for synchronizing model and calibration table. So now we have obtained calibration tables. The next step is to basically apply the trained models and calibration tables to the new data set. So in real world scenario, probably this part in a dark green rectangle will be a separate workflow, because usually you train a model in one workflow, you assess it, if it's fine, you deploy it, and you deploy it into another workflow. But for the sake of this demo, we are going to have everything in one place, in one workflow. So what's happening here? So the input for the next part, for conformal prediction loop, is the same as the output of calibration loop. So we feed the models and calibration tables here. And in the settings, you just have to set up the column that will be used for synchronization of the model and calibration table. I guess in most cases, you don't have to even set up anything here. It will fetch up everything automatically, but in case you are using some different way of synchronization, you have this flexibility. So then we doing slightly reverse process. Then we deserialize in the model in order to obtain the model from the cell. We feed it to a proper predictor, and then we feed the new data, or in our case, the test data set that we obtained in the first partitioning part here. Afterwards, once we get the predictions, again, please pay attention that we must have class probabilities in order to calculate p-values. Then we proceed these results along with the calibration table that is synchronized to the model to conformal predictor node. Let's see the settings of this node. So you need to set up the target variable, fairly simple. And then the settings are very similar to calibrator node. So you can select whether you would like to keep all the columns, all input columns, or you can pick just one ID column. And if you want to, you can include the rank column because it's not always actually useful. However, if you want to, you can include it. So let's do this. Then the p-values are calculated. So as Greg explained, in order to calculate the p-value, you need to take one sample. You need to get its class probability. You need to insert it into calibration table, resort the table one more time, get this sample rank, and then divide this rank by the number of records in the calibration table plus 1. Then you will calculate the p-value. And as long as we have two classes, we will have two values for p-value for each class, obviously. So this is how it looks like. For example, we have this sample that is that belongs to class 1. However, it was predicted as class 1, so we have a rank for class 1, p-value for class 1, and the same we have a rank for class. Sorry, it was class -1, -1. Then we have the same for rank 1 and p-value for class 1. And we repeat this process for every model and consequent calibration table. So this is actually what Greg described. This is a cross-Mondrian validation. And finally, in this conformal prediction loop end node, we aggregate the p-values and ranks by median function. So that's it. We have aggregated p-values, so we can go straight to the prediction. So in order to set up the desired error rate, you have to use this conformal classifier node that basically will assign the classes based on the p-values that you provide. So the settings are pretty straightforward. You just set up this error rate, and you can select what will be the output type of the classes. So there are two options. It could be a string format, or if you deactivate this checkbox, it will be a list. So obviously, if you have a multi-class classification, sometimes it will be easier to use representation as a list. However, how to find the best error rate for your data set? So for this purpose, I would suggest you to use another method or this optimization loop pattern. So what we are doing here, so we set up the range of the desired error rates. So the start point is 0.05, the stop value is 0.3, and the step is 0.05. So we would produce six sets of predictions. And we are going to use brute force algorithm in order to get all possible combinations. So here we just overwrite error rates with this flow variable, and then we run this loop. Inside the loop, we have the last node in conformal prediction extension that is called conformal scorer, and this node basically calculates the efficiency and validity values for the predictions. So the scorer node settings fairly simple, and they are very similar to any other scorer node in KNIME. You have to provide the target column and the column with predictions, or in our case, it's class column. And it works with both presentations, result presentations. It could be string or it could be collection. It's up to you. If you would like to get another metrics, you can activate this checkbox, additional prediction information, and you will get some other statistics, and we are going to include it. Then we deliberately add additional column with current error rate for this iteration, both for scores and for predictions. And also we are plotting bar charts of the predictions in order to see the visualization. Okay, so this loop is executed. Let's see what kind of results we might obtain. All right, so here we see the set of bar charts representing the predictions. So T, blue, stands for target. M, orange, stands for model prediction. In our case, it is random forest prediction. And CP, green, stands for conformal prediction. So here we have the following. So as long as we are quite strict and the error rate is equal to 0.05, we have a lot of uncertain predictions. So it means that, yes, these samples belong to what we have seen before. They belong to applicability domain. So it's something that belongs to class 1 or class -1, but the algorithm is not certain. It cannot distinguish between two classes. And we also have some single class predictions, and I believe these single class predictions, they are very very certain. So in this case, we have quite high validity values. Then we are getting this parameter loose. So now we increase the number of errors, which means that now the single class prediction amount of single class prediction increases while the mixed class prediction decreases. So if we repeat this operation, the predictions would follow this strategy. So more single class predictions, less mixed class predictions. And at some point, we can get in the following situation. So as you can see, now we have some null predictions. There are just a few, but anyway, it means that given the error rate equal to 0.25, we have quite high efficiency value. It means that we have a lot of single class predictions, no matter they are right or wrong. We don't have that much class predictions, but at the same time, we start getting null predictions. So algorithms say that probably these predictions could be out of the domain applicability. And again, if we increase the error rate even more, we will start getting more null predictions. So this could be one method of getting the idea what is the proper error rate, how to find this balance. So probably you should stop decreasing the error rate once you start getting null predictions. Another way to do this is to probably plot this kind of plot. So we have a efficiency validity level plotted against error rate. So what is going on here? So once we say the algorithm, we tolerate only 5% of errors, we have extremely high validity. So it means that most of our predictions probably belong to mixed class, but it means that they are inside the applicability domain, and we are not that sure about single class predictions. And obviously we have quite low efficiency level, but once we start increasing the error rate, we start getting higher efficiency while the validity goes down. So another suggestion is to probably find the points when they start intersecting. Or, as we have discussed in the previous distribution, you can take that part when we have this kind of band, when we start getting null predictions. Yeah, and so my suggestion in this case is to use this 0.17 value for error rate, and what kind of predictions we might have here. So I build this component with the visualization. So basically what we have here is conformal prediction metrics. This is what conformal scorer produces. Model prediction metrics, this is what binary classification scorer produces. Maybe it makes sense to inspect every single sample if you have some background knowledge or you're expert in this area and you're interested in some specific sample. And finally, there is some kind of a mixed confusion matrix when you see the distribution between real target values, model prediction, and conformal predictions. So yeah, I guess this is the end, and a short conclusion. So I guess the main three benefits of conformal prediction is that it's agnostic to the model you're going to use. It could be random forest, neural network, whatever. It still produces sustainable predictions for unbalanced classes. And another benefit is that user might set up the desired error rate. Thank you.
Thank you very much, Artem, for the nice demo. So I would say we just dive in right away in the questions. I will start with Greg. There were actually twice. Let's start with the simple ones about the data set that it came up twice, and also how to download the workflow. Maybe we start with that one, Greg.
Okay, the workflow, it's on the KNIME Hub. So if you go to the KNIME Hub and you Google for conformal, or not Google, search for conformal prediction, you will find it. The name of it is Conformal Prediction Workshop by Redfield.
I can also actually show that spontaneously.
Yep. And the data set, we forgot to save that with the workflow. Artem, could you upload a version of the workflow that has the data set in it, please? Or did that not work for you?
Yeah, but I believe this version should contain the workflow inside, because this file reader node has the relative path inside the workflow. So could you please check? And I will double check as well, but I'm almost sure that I have uploaded the version with the data inside.
Okay, so just what I did is I went to the KNIME hub and typed conformal prediction. And this is then the conformal prediction workshop by Redfield, and this is the workflow that you find on the KNIME hub. So I went to hub.knime.com. Okay, then I think also another very good question more on the methodology side. So this would be for Greg as well. Could you reiterate the difference between the training, calibration, and testing set?
Sure, I can do that. Artem, before I do that quickly, Artem, I didn't see it with the workflow that's on the hub, at least not the version that I found when I searched.
Okay, I'll double
okay,
check.
The difference between the sets, when you traditionally think of a machine learning model, you take your data set and you split it into a training and test sets. And then what we do when you do conformal prediction is we further split that training set again. So we split it into something that's called, sometimes it's called a true training set. I was lazy in my slides and I just called it training set still. So we split it into training and conformal. I'll just pull up the picture again so you can see that, what I'm talking about. If there's anything more for, so this is the thing you just saw Johnny show. This is the picture. So we split the training, the data set into training and calibration, and then into testing, and we saw this in Artem's workflow. And then inside that second loop, we split the training calibration set again into the training set, which is actually used to build the model. So that was a random forest model in Artem's case, and then the calibration set that's used to do that calibration table. So really there's these three sets. There's the training set, which is used for building the model, the calibration set, which is used for calibrating the conformal predictor, so actually making the conformal predictors in the end, and then a test set just to make sure that you have a sense of how good the model is in the end.
Thank you, Greg. So the calibration set is really special or unique to the conformal prediction algorithm.
Yes, yeah, absolutely.
Great. Artem, do you have any news for us, or shall I fire up a next question for Greg?
Yeah, I just need a couple of minutes.
Yep,
Yeah.
so I got another question for Greg. So Fabian Kaiser actually asks, why aren't you performing a hyperparameter tuning inside of the conformal calibration loop? So that per each loop of the conformal calibration loop, you get the best hyperparameters. Would it be bad to do it?
So no, it absolutely would not be bad to do it, as long as you're not looking at the calibration set when you're doing that. So as you do hyperparameterization or hyperparameter optimization, just using the new training set inside, there'd be absolutely no problem to do that. We did not do that here because the hyperparameters that we used for the random forest are ones that just tend to work reasonably well in data sets of this size or of this type. So I just know that from experience. So we didn't do hyperparameter optimization. We absolutely could have done that and there would have been no problem. It just would have made the whole process take even longer. But there's no statistical problem with that. There's nothing wrong with doing that.
Thank you.
If you have the patience.
Time. Fabian Kaiser also before asked a question which I thought was very good. Artem already answered it, but I thought I'd just bring it up again here because I think it's a very valid point, because he said if there are any plans for the implementation of different non-conformity measures. And right now, as we said, right, we are using the probability coming out of a model, but you could, for example, also imagine to use the distance to the nearest neighbors or things like that. And I think that's a very interesting point, right? Because in the end, what you want to do is you want to rank somehow your tables, but you don't need to do that with using the probabilities coming out of the model. And maybe Artem, you can comment for everyone again on this one. I think it's a good question.
Yeah, so as long as this is like a first implementation, we decided on focus on the most straightforward metrics to apply conformal prediction. So probably you can use some kind of a hack, like renaming any metric that you would like to use and feed it to the current implementation of nodes, and it should work. But of course, if there will be a demand, maybe you could contact us. We can have a conversation, and we would be glad to update these nodes if there will be an interest from the community.
Thank you very much. Perfect. Let's look, what else do we have? So there's a question of actually how to export the model built with that method.
I think I can answer this question. So if I understood correctly, so you generate the model and you generate the calibration table, and you have to keep this pair. So I've been showing how you can use it in loop. So you can aggregate everything inside the loop, and then you can store these two tables, tables with models and tables with calibration tables. Or you can store the calibration table and the model on every iteration step. It's up to you. It depends on your use case.
Thank you. And then there's one from Paulo, and he's asking if I get a prediction, first toxic with conformal prediction, and another prediction, toxic and non-toxic, can I say that my first prediction is more valid than the other one? That's a brain teaser. Maybe Greg wants to answer this one.
Of course, Paul is asking hard questions. So I believe that the answer to this question, so it depends on what you mean by valid. The prediction in either case is valid, right? That is the prediction that the model has generated, or that the conformal predictor has generated. So either one is perfectly valid from a statistical point of view. One of them is more useful than the other, right? So if I give one row to the predictor and it says single class prediction toxic, and I give another row to the model and it gives a prediction set that has both toxic and non-toxic in it, I can do more with the single class prediction, right? I can actually act on that. The prediction that gives both classes, what that tells me is that the model is not really able to distinguish between the two answers at the error threshold that I provided. So if I said my error threshold is 0.1 and I get both of those, it means that it can't give me a response, or it can't give me an answer with really a 90% confidence for that. It can't give me a single answer with a 90% confidence, so it gives me both.
And that might also be just a hint to do a follow-up experiment or something, right? So that could also be something interesting there. You never know.
Yeah, I mean, there's certainly the things that generate the multi-class predictions. It is clear that those are instances where the underlying models, the underlying random forests in this case, are really not so sure about them, right? There's just a lot of uncertainty.
Yeah. Which could also make them interesting.
Yeah.
So one last question, I would say. We're perfectly on time. It's the only question that's open, actually, so that's perfect. So could you please explain a bit more about the confusion matrix of conformal prediction?
Yeah, sure. So probably I can I share my screen one more time in this case? So obviously this is like a not true confusion matrix as we understand this. I just wanted to, I've been thinking about this a lot, and I just wanted to see all the possible combinations of both target, model, and conformal prediction. So what we have here, so in target column, we have only -1 and 1 values, which stands for two classes that we have. The same is for target, for prediction, for model prediction. So model can only distinguish between two classes. And here we can see, so if we get rid of this column, we will get kind of a typical confusion matrix when we compare the real values with the predicted values. But also we have added another class of predictions, conformal predictions. And here we have even more values because we might have null classes, we might have mixed classes. And here we just calculate the number of samples that belong to this group. So, okay, we take the target class -1. We calculate how many samples we have for target that -1 that was predicted by model as -1 class, and it was predicted by conformal prediction as -1 class. Then we go to the next row. It means the real target class -1 when it was predicted by model as class -1, but when it was predicted as class 1 by conformal prediction. And I believe somewhere in the end of Greg's presentation, he has more simplified representation of the same or very similar table. So I guess you can also look at the slides because they are going to be available. I hope I explained what I meant by this confusion matrix.
Yeah, I think it's clear, and that also really is a good reminder to everyone. So we will share the slides. You will get an email with the slides. We will share the recording. And again, the workflow is available on the hub. So really feel free to take a look or think about it a little bit more. And with this, I really want to thank you, Artem and Redfield, for those great notes. And also thank you, Greg, for introducing the methodology today. And thanks everyone for joining. Hope to see you soon. Don't forget the webinar next week of Redfield as well. Bye-bye.
Goodbye. Thank you for attending.